Hello, my name is Yanofsky. This is Theoretical Computer Science. We're going to do the homeworks for section 1.2. Okay, and again, I have to stop you. Hello, do not just watch this. First do the homeworks on your own. Okay, and once you do the homeworks on your own, you'll be able to check your answers here. But if you're just going to watch this, it's worthless. Okay, you watched me do problems already. I did problems in class. Okay, this is not what it's all about. The thing is for you to struggle and get through the homework on your own and then check the homeworks while you're here. Okay, the first problem is problem 1.7. Okay, and basically it says give state diagrams of NFAs with specific number of states recognizing each of the following languages. In all parts the alphabet is 0, 1. Okay, so let's do it. There's 1 through H, but a lot of them we did already. Okay. W such the language ends with W 0, 0. I'm assuming you have the book, so I'm not going to write it up, and we're going to go a little bit quicker. 1.7a. It ends with 0, 0. That means I don't care what it starts with, okay, but at some point you're going to have a 0, 0, and then you go like that. Okay, that's non-determinism over there. You never know what the 0 is. And that also uses 3 states. Ends with 3 states. 1, 2, 3. Okay, great. Notice if you have more than 0, 0 here, you die. Okay, let's do B. Okay, W contains at least 3 1s. W contains at least 3 1s. Oh, I'm sorry, I'm wrong. The language of exercise 1.6c, which is W contains the substring 0, 1, 0, 1. So basically you have 0, 1, 0, 1. Okay, it contains it. That means once it contains it, then you should accept it and you should stay there no matter what. Okay, 0, 1, 0, 1. Okay, now you never know if it does contain it or not, so you have to put this on. Okay, and each point you're waiting to check, will it contain it? Now, if this was deterministic, then sometimes you'd have to go back. Okay, but this is not, and you know, if you had a 0, 1, whatever, you'd have to go back. This is not deterministic, and by not being deterministic, at every point you're just staying here to see if this is the beginning of 0, 1, 0, 1, or going. So you do it like that. Okay, 1.7c. Okay, the language of exercise 1.6l. W contains an even number of zeros, or as soon as you see the word or, you're going to split up. W contains an even number of zeros or exactly 2 1s. So when you see the word or, you automatically split like that. Okay? Because you're going to try this and you're going to try this. Okay, so contains exactly 2 1s. That's pretty easy. So it contains a 0, I'm sorry, a 1 and a 1, and it's an accepting state. That's it. Okay, if there's any zeros in here, it automatically dies. Or, what's the other thing? As soon as you see the word even, you know that we're going to have that parity checker again. Okay, so W contains an even number of zeros. So let's see. Well, no zeros is an even number of zeros. If you contain a 1, 1, 0, you get not accepting. If you have another 0, you are accepting. Okay, but this is allowed to have 1s also. Both of them are allowed to have 1s. And so we have that. Okay, next, D, the language with 2 states. The language, all it has is just 0. So we actually did this in class. That's it. Okay. It's a stupid language. It just has one word, and that word has just one letter, and there we have it. Okay, let's do some more. Okay. E, the language 0 star, 1 star, 0 plus. We did this in class, but that's okay, because we do the harder problems in class. We leave the easier ones to you for homework. So what is it? 0 star, 1 star, 0 plus. And that's an accepting statement. Okay, and that has 3 states. Okay, F. The language 1 star, 0, 0, 1 plus star. 1 star, by the way, the empty word's accepting, so we know that. Okay? And then 0, 0, I want a 0, and then I want a 0, and then I want a 1. Okay? I should have at least a 1. 0, 0, 1. At least 1, 1. Go like that. And that's it. That is it. And that's 3 states. 1, 2, 3. G. The language with epsilon. We did this in class, but it's worth doing again. Okay. And finally, H. Okay. That's it. Okay. So that's 1.7. Okay, great. Next is 1.16. Notice they're out of place. They're out of order. The homeworks are out of order. Well, that's because we do things slightly out of order. Okay? We did easier things first. So, the next thing is as follows. Okay, this is 1.16, where we have to change an NFA into a DFA. And this is the whole thing that we did this in class, but that you might think NFAs are so much more powerful, but no, they are just as powerful as DFAs, just the DFAs are more complicated. Okay, so this is a two-state things. There are 4 subsets of two-state things. That's the empty set, 1, 2, and 1, 2. Let's just do it. Okay, if you're in state 1 and you see an A over here, you go to A and B. I'm sorry, you go here, 1, and to 2, and so you go here. That's if you see an A. Okay. If you're in state 1 and you see a B, you go to 2. That's pretty simple. Okay. If you're in state, let's do 2, and you see an A, you go to state 1. No. If you're in state 2 and you see an A, you go to state 1. Let me just make sure I have the right problem here. If you're in state 2, that's a B. Sorry, that's a B. If you're in state 2 and you see an A, you go to the empty state. Okay, because you don't go anywhere. If you're in state 2 and you see a B, you go to state 1. State 2 and you see a B, you go to 1. Okay, and finally, if you're in state 1 and 2 and you see an A, then this one's going to stay here and going to go there. So that's over here. If you're in state 1 and 2 and you see a B, you're going to stay here also. Okay. Finally, if you're in state the empty state, it means you're nowhere, then no matter what you see, you stay there. Okay, so that does that. Okay, what's the starting state? This is the starting state. What's the accepting state? Anything that has a 1 in it is an accepting state. And we're done. I think the only thing okay, that takes care of that. Okay, this is a lot harder and we're going to make mistakes, but we're going to be very carefully. Okay, you're in the empty state. So this has 3 states. There are 8 possible subsets, so we do that. No matter what you see, if you're dead, you stay dead. Okay? Let's do some other things also. Question, what's the accepting state? Well, here it's a 2, so here anything that has a 2 in it will be an accepting state because it means you can get there. Anything that has a 2 in it will be in an accepting state. Okay, hard part. What is the starting state? Okay, now notice what we have here. If you're in 1, you're automatically in 2. That's an epsilon move. If you're in 1, you're automatically in 2. So you can't say that the starting state is 1 because you can never be just in 1. You're automatically here. So the starting state is here. Okay, let's do it. If you're in 1, then you're automatically in 2, and you see an A, okay, then where are you going to go? The 1 is going to go to 3, so it's going to go to 3. The 2 is going to go to 1, so it's going to be to 1 and 3. Okay, but you can't just be in 1 and 3. You're automatically in 1, 2, and 3. So if you're in 1 and you see an A, you got that. Okay, great. If you're in 2, if you're in 1, then you're automatically in 2, and you see a B, then you die. Then you die. You're nowhere. Okay, great. If you're in 2, you're not automatically in 1, but if you're in 2, just 2 of itself, and you see an A, you go to 1, which then brings you to 2 also. Every time you're in 1, you're automatically in 2. So again, if you're in 2 and you see an A, you're automatically in 1. And when you're automatically in 1, when you're in 1, you're automatically in 2. So if you're in 2 and you see an A, you become 1 and 2. If you're in 2 and you see a B, he dies. That's it. You just die. 2 goes to B. Okay. Things are getting a little bit messy in here. Maybe there's a better way of arranging the states, but I didn't see it yet. Okay? Great. If you're in 3 and you see an A, if you're in 3 and you see an A, then you automatically go to 2. That's it. So if you're in 3 and you see an A, you go to 2. If you're in 3 and you see a B, then you go to B, 2, and 3. Great. Let's do more. 4 more to go. By the way, these get more complicated, so let's do it carefully. If you're in 1 and 2 and you see an A, look what happens. The 1 goes to 3, okay? and the 2 goes to 1, and if you're in 1, you're automatically in 2. So the 1 goes to 3, so you have 3, and the 2 goes to 1, which is automatically, so if you're in 1 and 2, you automatically like this. That's an A. Okay, let's do a B. If you're in 1 and 2 and you see a B, it seems you die. Seems you die. He doesn't have any place to go, and he doesn't have any place to go. So 1 and 2, and you see a B. There you go. I changed the color just to, I don't know if you can see the difference in the color, but okay, good. Next, you're 1 and 3. Now, if you're in 1 and 3, if you're in 1, you're automatically in 2. So you're 1 and 3, and you see an A. So the 1 goes to 3. The 3 goes to 2. No, hold on. If you're in 1, you're automatically in 2. So let's go through this. So I have to worry about 1, 2, and 3. The 1 goes to 3, the 2 goes to 1, and the 3 goes to 2. So if you see an A, you're in all 3. If you're in 1 and 3 and you see a B, what happens? Okay. If you're in 1 and 3, you're automatically in 2 also. So we have to worry about all 3. So if you're in 1 and you see a B, nothing. If you're in 2 and you see a B, nothing. If you're in 3 and you see a B, you're in 3 and 2. Okay, that's good. Okay, I'm getting sick of this. Okay, if you're in 2 and 3 and you see an A, if you're in 2 and you see an A, then you're in 1 and 2. And if you're in 3 and A, you're in 2. So this goes to 1 and 2. 2, 3, goes to 1, 2. That's an A. Let's do that. If you're in 2 and 3 and you see a B, okay, this goes nowhere, the B, then you go to 2 and 3. So 2 and 3 takes it to itself. That's a B. Okay, finally, you're in all 3 and you see an A, so this A goes to 3, this A goes to 1, and this A goes to 2. So you see an A, you go to all 3. Okay, great. And if you see a B, then you go to 2, 3. Okay. It's ugly, it's complicated, but it's right. Okay, great. Let's do some more problems. We'll do it in 1 second. Okay, the next 3 problems are the 3 problems that we saw. Union, concatenation, and star. Okay, and so I wrote up the problems already, and we can just do them. The union of the language W, such that W begins with a 1 and ends with a 0, and W contains at least 3 ones. Whenever you see the word union, it's very simple. You just do this. The union means all the words that belong here or here. So what you do is you start off. Those words belong in one and in the other. Okay, and you try both of them because you want it's either in here or in here. It could be in both, but that doesn't. Okay, now we have a simple problem. The union W begins with a 1 and ends with a 0. We did that in class already, but let's just do it over here. We did it as a deterministic one, but we can do it a lot faster as a non-deterministic. Begins with a 1 and ends with a 0. That's exactly this. Okay, starts with a 1. I don't care what happens in the middle. Ends with a 0. And here's the non-determinism. You try both ways. Whether every time you see a 0, you say, "Oh, is this the last one, or is this just in the middle?" Okay. Okay, great. And W contains at least 3 ones. That's simple. 1, 1, 1. Okay, at least 3 ones. If it contains 3 ones, then you stay there. And I don't care how many zeros there are. Okay, that's that. Okay, great. The concatenation means bring 2 languages together such that the beginning of every word is here and the end of every word is here. And so we have this thing. The length of W is at most 5. We saw that already. That's simply this. One, 2, 3, 4. Okay. Now usually that's an accepting state, but now we're concatenating it. So we want more things. We want an epsilon move, and here we are. Every odd position of W is a 1. So the first position is a 1. The second position, I don't care, etc., etc. Okay, so that's this thing. Every odd position is a 1. By the way, this is non-deterministic. Okay, so we don't care. Question? Okay, I'm in the middle of taping. Okay, next. The star of W. W contains at least 3 ones. So let's just do that. That's contains 1 1, contains 2 ones, contains 3 ones. I don't care about zeros. Okay, even it can start with zeros. Okay, but that's not the star. That's the original thing, and this would be circled. In fact, it will be circled. Okay, but then we have to have, guess what? W contains at least 3 ones. The star of that is accepted. So the starting state is accepted, and then we go from there with an epsilon move. And then we have to go from the end back. But the truth is you don't really need that, but we'll do it because it's typical. Okay, so actually that's an epsilon move. Okay, but there's a problem here. Okay, anyways, that's it. We're finished. That's it. Okay, one more problem here. Let's read the problem. It's 1.11. 1.11. And the book is here. It says as follows. You ready? 1.11. Prove that every NFA can be converted to an equivalent one that has a single accepting state. Okay? And how does that work? So let's say you have an NFA. And it's got a starting state, and it's got a finishing state, and there's arrows here, and there's arrows here, and there's arrows here. And it's got 3 different accepting states. Okay? What I like to do is make another finite automaton that has exactly 1 accepting state. So here's what I do. I make one thing over here as an accepting state. That's a new state. I add in a new state. Okay? And then I make epsilon moves from here to there. Okay? And I erase these because they're no longer accepting states. Now, if you ever land into one of these 3 things, you automatically go here, and that's your accepting states, and then you're finished. Okay? So that is section 1.2. Okay? You can formalize this, etc., but it's nice. We are going to use this idea later on. Okay? Thank you very much. Next time, we'll see.